All right, I finally got it set. There we go. So today is the fourth of the 5 lectures on machine level programming. And today we're going to talk about data. In particular, we're going to talk about arrays, both one-dimensional and nested arrays, multi-dimensional arrays, multi-level arrays. We'll spend a significant part of the class on those. Then we're going to talk about structures and the interesting things you need to know about how structures get aligned in your code. And then very briefly at the end, we're going to talk about floating point assembly code, like floating point registers and instructions. Okay, so if you're familiar with this in C, you've got some type definition. Okay, and then some array named A, and it has L elements. Okay, and so we think of that as if this A starts here at this X right here, then the fact that in this case there's 12 of them, and they're each a car, so they're each a byte long, means this whole thing ends at X plus 12. Okay. Another example, we have ints. So ints are 4 bytes, and so each of the elements is going to count for 4. And there's 5 of them, so that's how we get all the way from X to X plus 20. And doubles are, since they're 8 bytes, and there's 3 of them, you'll get up to X plus 24. Okay? Well, what about this one? Okay, well this is, it's a car, but it's not really a car, right? It's a pointer to a car, right? So it's effectively a string. Okay, so what's allocated here is room for 3 strings, right? Three pointers. These strings. Okay, so now, given that, so let's look at the example here where we have, again, our integer array of size 5 integers, and it's going to be the zip code digits, or the course number digits, 15213, and it's laid out as accordingly. And now we want to look at some of these references. So suppose in the program you had the reference, val of 4. Okay, that's going to be of type int, and it's going to be 0, 1, 2, 3, 4. It's going to be this 3, right? So that's what's shown there. What about if in the program you just wrote val and nothing after that? Well, that's going to refer to this entire array, so it's going to be a pointer, right? So the address at the beginning of the array, pointer to a bunch of integers, and in this case, its value is going to be what? X, right? Okay, now in C, you can do strange things like do arithmetic on these pointers. So if I do val plus 1, the type is still int star, but where does that jump me to?
X plus 4.
X plus 4. Okay? Because it knows that you're sort of skipping ahead 1 in this counter here. So what about this one? So we have val 2, but then we take the address of that. So what is that going to return us?
X plus 8.
See that? X, that's right, X plus 8. All right, and what about val 5? That's, intended to be an integer, I guess, but what's going to happen? It's off the end, right? I mean, here's 0, 1, 2, 3, 4, so val 5 is this thing here, so, who knows what that's going to return, right? What about this one? So val plus 1, and then we want to dereference through it.
5.
And what about just val plus I? Okay. So in general, val plus I, so that was val plus 1, we saw the example earlier. In general, since each of these things are ints, then for every I, we're going to plus 4 more. So it's equivalent to X plus 4 times I. So any questions on those? Yes?
So if you do val plus 1 but val values of type, say, long, would it increment by 8?
Yes.
Okay.
Yes.
I know it's not very meaningful, but if you wanted to do x plus 1, like if you wanted to get the value of x plus 1, how would you do that?
So I guess, let's see, if you took, yeah, that would be hard to do in C, right? I mean, I guess if you maybe cast this, like assign this to just a normal integer, yeah. Yeah, that'd be true. I mean, it's easy enough to do in assembly, but that'd be tricky to do in C. Does anybody have a bright idea on how you might do that?
We'll make a char pointer to the x plus 1.
Okay, that works. Okay, so you have a car star. Get rid of this thing, car star. And you originally assigned that to x, so var y. You originally started at x, and then you can add 1 to that. That's a good answer. Yes? Yeah, if you had constructed a separate data type that was a union of this and say a car star, yeah, you could go back and forth. That's true. All right, good. All right, so here's another example. So we have, we've defined this thing called zip digits, and it's 5 long, and so we can say that, CMU, the zip digits are 15213, MIT, Berkeley, and so forth. And if you see that how that gets laid out in memory, as before, for any one of these, it's consecutive 20 bytes, right? Now, there's no guarantee that these are, adjacent in memory, but in this case, they happen to be. When this was allocated, the MIT one started immediately after the CMU one, and so forth. Okay. Yeah, so not guaranteed to happen in general. That's what's saying there. Okay, but in this case, it happened to happen. It would work out that way. Okay, so now let's suppose we had this routine get digit. So you pass it a zip dig and a digit, and it returned the digit of that zip dig. Okay, so if you pass it CMU and the digit 1, it would return the 5. Right? That's the goal. So by convention, right? These are both integral arguments. So this first argument is in RDI. The second argument is in RSI. And so that's kind of what's annotated here. And so in order to extract that digit out, you'd have this code here, right? So what is this doing? Well, again, if you recall, this is you take this and you take the product of these two. So this computes what's shown here, right? RDI plus 4 times RSI. And so that is indeed the start plus a multiple of 4 times however many the digit ends up being, right? You move that into EAX, which again is the low order half of the return register RAX. And so that's how you get the answer. So the nice thing is this entire procedure was just the one instruction. Okay, any questions on that? Good. Okay, so let's suppose you have this loop. Okay, so we're going to move 0 into EAX, and then we're going to jump here. We're going to compare 4 versus what's there, and we're going to do this branch and come back up here and then add 1 to this address calculation. So if this is, I guess this is Z initially, and we're going to add 4 times whatever this address thing is, and then we're going to add 1 again, and do the comparison and drop out. So anybody have idea what this is doing? It's kind of hard to get through at once, so give you the hint. Okay, so here's the comments that we just went through. What we're doing is we're stepping through this array. That's array where the elements of the array are 4 bytes. That's where we're stepping forward at a time. And then we're comparing to see if we start at 0, we're comparing to see how it compares to 4, and if less than or equal to, we go around the loop. Okay, so it's basically this. We run through the 5 digits of the zip code, and we just bump up each digit by 1. Okay. So over the course of this course, you should get more and more facile being able to do what we just did. We sort of look at the assembly code here, maybe draw yourself a little annotation style like here, and then from that think back. Okay, what's the C code likely to do? What's this doing? What is this doing? Okay. Okay. So because there's always so much, people get tripped up so much about arrays and pointers and how they work and so forth, we're going to use this class also to drill a little bit more on your understanding of these two things. So here we have 2 example declarations. We have this one and this one. And what we want to know is for each of these 2 examples, will the code compile? Is it possibly a bad pointer reference? And what is the value returned by size of? Okay, so if I have this declaration and I refer to A1 in my program, will the compiler complain? No, perfectly good, right? So this compiles. What if I reference, if I do a dereference, if I say star of A1, is the compiler okay with that? Yeah, that's fine. Is there an opportunity that I'm going to have a bad pointer reference if I start referring inside to this declaration? Another way to think about it is what memory has already been allocated, what memory hasn't been allocated, just by this declaration. So by this declaration, you get this thing that has 3 ints, space to hold 3 ints, right? And so if you refer to any of the elements in this array, you'll be fine, right? Everything's allocated. It may be garbage inside if you haven't initialized it, but at least it's not a bad reference. This is fine. So no. And what if you reference through A1? Okay, well that's just another way of referencing the start of the array, so that's fine as well. Okay, what about the size? What is the size of if I say size of A1, what am I going to get? Yes? Right. Okay, so if the size of it's 4 bytes, we'll get 12. Okay? What about the size of this item here? And everything in this class is on a 64-bit architecture. Well, this is a pointer, right? So that says 8 bytes. Okay, what about this one here? Int of A2. What is that? Well, that's just something that's a pointer, right, to an int. All right, so what's been allocated by that declaration? Certainly the pointer. What about the int? Has it been allocated? No, right? You haven't. I mean, it's just a pointer. You haven't actually allocated what it points to, right? I can declare a pointer to be a pointer to some huge structure that I haven't allocated at all. It's fine. It's a perfectly legitimate declaration. It's just not allocated memory yet. Yes.
Going back to like the size of star A1, like why is that a pointer?
So you have A1, right?
Yeah, and then you dereference it.
And you dereference it. So that's a good point. Okay, so you get actually the first element of it. You're right. Okay, so this should be 4. Good. Good. Okay. All right, so this is going to compile. A2 is going to compile. What about star A2? You refer to that. That should be fine, right? A reference to A2 is fine. But again, this reference through A2, what's here may not have been allocated yet. Okay, what about size? So the size of the entire thing is what? It's a size for a pointer. But if I dereference it through, what's the size going to be? It's the size for an int. Okay? And if I did this right, then it should match this chart. Okay, good. And this is sort of showing pictorially, right? The picture I just drew. This is saying that if the yellow is allocated stuff and the gray is unallocated, you can see you have an allocated pointer but an unallocated int here. Whereas when you define it this way, you have 3 allocated ints. Okay, questions of that? Yeah.
Is A1, why is that 12 unless A1 is not a pointer?
If you do the size of A1, so A1 is a array of size of 3 integers.
Oh, it's like a pointer. Is it not a pointer to an array, or is it itself the array?
It's the in some sense it's kind of both, right? It just depends on how you're referring to it. Right? So if you put in the size of command A1, it will interpret that as saying, oh, what I want to know is what is the size of this of this array, right? It'll be 12. Okay. All right. Other questions on that? Yeah.
So A1 is stack allocated, right?
Yeah. So this will be stack allocated, and then when you do, like, if you call malloc or something to actually allocate what things point to, then it'll be heap allocated.
If you make another stack allocated array, like you have A1 brackets 3 and then you have A2 brackets 5, then can you set A2 to equal A1?
A2 equal A1. So in that case, it'd be referring to the pointers, and so yeah, you can.
Okay, so those are pointers to the stack. Is that how that works?
Those are well, you so that's just kind of a different question, right? So depending on where the thing is is allocated. So if you're in the middle of the program and you do that computation, if this is allocated on the stack, then it will point into the same place in the stack this was before.
Okay.
Okay. Now it may decide that if like this 3 was really big, then it may decide to do it on the heap, right?
Oh, it will have to decide. You can change where to put it based on how large it is.
Yeah, right. Because it makes judgments about these things, right? Okay. Good. All right. So okay. So here's another example. All right. So here again, we have A1 of 3. And now we want to look at not just whether A1 and star A1 is, but like a star A1. Okay, what is that? Was that legal or not? Okay, so we've already done these. This is the same example as before, right, for these two. But what about the new ones? So if I have star star A1 in my program, will that compile?
Yes.
I think the answer is no, right? Because once you get to, right, once you, this is type integer, there's no, it's not a pointer, so you'd be trying to dereference an integer. Okay, what about this one? So if I have, so this one's kind of interesting. So this is saying I have, what's A2? A2 is an array of 3 things that are pointers to integers. Okay, so it actually looks like this, right? You've got the 3 pointers, and each of which point to integers. Okay, so now if I do the double dereference of that, what's going to happen? Right, the first reference of A2, will get me to this pointer. The next one will get me to the int, and so this should be okay, right? But on the other hand, it's going to be bad, right? Because these haven't been allocated, all right? This is an interesting case. This is saying I have because of these parentheses, I have a pointer to an array of 3 integers. Okay, so it looks like this. I have a pointer to an array of 3 integers. Okay, none of which have been allocated, and so therefore the size of this is just the size of a pointer. Right? If I dereference once, I get to here. I get to this whole thing. So the size of this is what? Any guesses? Gets tricky to hurry, right? Nobody has a guess. Yes?
Is it size 12?
Yep. Okay, so this ends up being 12, but if I dereference again, then I'm looking at something that's size 4. Okay? So these are, the reason we cover these is that they're confusing, right? And the more, and I don't expect you to sit here in class if you haven't thought about these things before and be able to figure it all out. But I think that if you look at problems like this, after class or look at them in the book, look at these slides again, and get to the point that you do understand how to fill in a table like this, then you'll have learned it. Okay, and this kind of thing is fair game for an exam question, right? Okay. All right, so let's move on to multidimensional arrays. The normal way we think about multidimensional arrays is with a nested array. So like here's an example of a 2-dimensional array. So, you've seen this, I'm sure, before. There's some type, and there's some array name, and then you've got some number of rows and some number of columns. Okay, and pictorially you can lay it out like this. Rows this way and columns this way. The total size of this thing is just the number of rows times the number of columns times how many bytes you need to store one of these elements, type T, right? Now, important thing to note is that I have this 2-dimensional thing and I want to lay it out in 1-dimensional memory. So I basically have a number of different choices on how I want to do that. Okay, but the two that are the simplest to think about is that I lay out a row and follow it with the next row and follow it with the next row, or I lay out a column and follow it with the next column and follow it with the next row. Well, it turns out that the former is sort of the convention that gets used, and that's called row major ordering. And so that looks like what's shown here is that the first things that show up in memory are this first row, okay? And the next things that show up in memory are the second row. And finally, at the end, the last thing that shows up in this consecutive block of memory is the final row. Okay? Why do you care? Because you're going to have to address into or understand what's going on when the assembly code addresses into these arrays, that how it's doing the calculation to figure out where things are. All right, so let's look at this example. Let's suppose that we take our sort of one-dimensional zip dig thing, and we create an array of those of size 4. Okay, and so the effect of that is a two-dimensional array. All right, and it looks like this. So we've arbitrarily decided this starts at 76, and then it's going to be laid out consecutively. Each of these, as we know, takes 20 bytes, and therefore the 4 of them take 80 bytes, and that's how we end up with 156. Okay. All right. Good. Okay, so now how do we access things into it? So if we want to access an entire row, okay, then how do we get the starting address for that row? Well, the starting address for the row jumps by however many you need to jump, however many columns there are, times the size of the item. Okay, so that's what's shown here. So if I have a 10 columns, then this jumps by 10 times the size of each element. Okay, and so if I want to get to row I, then multiply that by I. And you can see, another reason why C index is starting at 0, right? That basically then I don't have to subtract 1 off the I. Right? So A sub 0 just naturally falls in here. And if I want the ith row, then it's I times C times 4. In this case, I'm showing an example where they're integers, so it's 4 bytes each. Okay? Questions on that? Okay, so now, so what does the assembly code end up looking like? So let's suppose that I want to get back just the zips, the zip code from one of these 4 places. And so what I do is I wrote this little C function that looks like this. Okay. And so what is the starting address? Well, we said the starting address is always, the index you have in mind. Index you have in mind times the size of each element, okay, times the size of each column. So if this is, okay. So we said this is 20 bytes, and so it's 20 bytes times the index, right? To get to, so in the case of 2, it's 20 times 2 or 40. So it's the starting address plus 40. Okay. So multiplying by 20, the compiler is smart enough to figure out how to do that in just 2 steps that don't involve an integer multiply. So that's good. The first thing it does is it uses our friend the LEA instruction. If you remember the addressing mode, what it's going to do is it's going to take this quantity here and add it to the product of these 2 things. Right? So that's equivalent, since I gave it RDI in both cases, that's equivalent to multiplying what's in RDI by 5. In this case, the index is what's in RDI, and so I get 5 times index here. And then I use another LEA instruction to first multiply that 5 again, because now it's sitting in RAX, by 4, so I get 20. And then I want to add on the starting address wherever PGH starts. Okay, and then I store that in RAX. So the net result is I get exactly the address I'm looking for. Okay? Any questions on that? Pardon?
How do we get 20 times index? Sorry, how do we get 20 times index?
Okay. So there are 5 elements in a row, right? Another way of saying that there's 5 columns, 1, 2, 3, 4, 5. And each element is a 4-byte integer. So 5 times 4 is 20. Okay, so if whatever this is, this location here is going to be PGH plus 20. This location here is PGH plus 40 and so forth. Okay? All right, good. So now let's suppose I don't want just the entire row, but I want an element in the 2-dimensional array. Then it's just a simple adjustment. I compute as before to get to the start of the row I'm interested in, and then I just need to jump over to the element within the row. So if I'm looking for the jth element in the row, then since again each element is 4 bytes, I jump over by j times 4. Okay. All right. Any questions on that? Yeah.
Yeah, what if you want to like you visit I equals 0 and j equals c? Will it get a1 0? Or will it like report a somehow like address the report?
It'll report. Yeah, it'll just report what's there, right? I mean, it probably won't complain. It probably will just return what's there in memory, right? It's similar to any time we go off the end of an array. It's just gonna, return what's there. We ask for it.
So like it will calculate the address no matter what the c or
Yes. Yeah.
and whatever is there.
Yeah. So in like some of these functions, if you give it a value that's an index that's way off the end, it will go ahead and calculate it and return what's there, right? So this is just an example. If you have this C code here, I want to return a particular digit within a particular index. And so if I give it, if I want PGH11, then it's going to return me this 5, and it's going to just do that calculation, very similar calculation shown before. The only difference is that if you recall, we said that it's 20 times the index to get to the start, and it's 4 times the digit within, the offset within to get to the next. And so you can factor out this 4, right? Because this 20 came from 4 times 5, 4 times C. And so it's always going to be the exact same 4, quantity 4. And so you can calculate like this. And that's what's done here, right? It basically first calculates 5 times index time plus dig, and then you multiply it by 4, and then add that, make that the address you add to PGH. Okay. Right. It's just a refactoring of this equation, right, where you pull the 4 out, and say this is equal to A plus 4 times I times C plus J. Right? And again, this 4 comes from int. If this wasn't an array of ints, if it was an array of something else, it would be the size of that item. Any questions on that? So this is also a multi-dimensional array, but it's done in a slightly different style. It's done as a multi-level thing. Okay, so here you can see that we defined this thing that's 3 pointers, and we've initialized it to our 3 different zip codes. Okay, so we had this zip digits for CMU, for MIT and Berkeley, and then when we created this university thing, we initialize it so that MIT was ahead of CMU. So that's clearly wrong. So we can fix that now. So this should go, these should swap, okay? But other than that, it's good C code, okay? All right. And so although we can think of this as a two-dimensional array, the addressing is very different because instead of being able to assume something about row major order, which allowed us to do this nice arithmetic calculation of the address, we actually now have to follow these pointers, right, to get where we want. And so that makes things more complicated, right? It ends up being, you take the, this part tells you if I have an index into this university thing, then if the index is 0, that means I'm interested in this guy. Index is 1, I'm interested in that guy. Index is 2, I'm interested in that guy. Since these are pointers, they're 8 apart, and so that's why you have to multiply by 8. And so this right here gets you this pointer, right? What's the contents of this pointer? Once you have that pointer, then you know where this whole thing starts, right? And in the CMU case, you know now you start here, and now you just want to treat this as a one-dimensional case and just index as we showed for one-dimensional. So the fact that these digits are all 4 bytes each, you multiply it by the number of digits you want to cross, right? So if I want the digit 1, again, it's just I return 5. Okay? So you can look at this code more carefully on your own. It's using a shift to do a multiply by 4 in this case, and it has to reference memory twice. So in general, it's going to be a slower way to do it, right? Much better to just not have to fetch a pointer to know where you want to access. All right, so any questions on that? And this is just saying the same thing. So before, in order to get the item, we did this address calculation, and then we fetched. Here we had to do this intermediate fetch just to get the pointer, and then we could eventually get the value itself.
Wouldn't the compiler not optimize to make the thing that you wrote the same as the previous one?
It's tricky, right? It could. The thing it doesn't know is that, you may have wanted these pointers because you're going to be changing over the course of the program, right?
Assuming you don't change that.
Yeah, if you don't change it, then, yeah, if it's sufficiently smart, it could figure it out. Yeah. Be interested to try it out to see if like you put optimization level 3, whether it would do that. I suspect it would take a pretty, I suspect not, but maybe. Okay, so here's an example where we have that illustrates different ways of indexing into code for indexing into matrices. So if I have a matrix that's n by n, but I've fixed n, so it's the compiler knows the size of n, so it's 16. Then I can write things like return aij, and the compiler is going to know exactly, can sort of compute that address right off the bat, right? It doesn't have to wait to find out how big, how many columns there are in order to do some multiplication. It just knows it's got to take this number, multiply by 16, add this other number, and so forth, right? So on the other hand, if we have variable dimensions, and so it used to be that you had to sort of do your own indexing, okay? That you had to put something like this in your C code that told the compiler, how to find this thing, okay? But GCC in the last, 4 or 5 years has now done the simpler thing, and it sort of allows you to write as you did when it was a fixed array, and it is now smart enough to know to do this. Okay, and the only difference is that you have to make it explicit in the declaration. You can't just get away with this form here, because then it really doesn't know what's going on. But if you say, n times n here. Okay. Yeah, okay, this is just what I was saying before, that basically if it's known 16 by 16, then it can go ahead and shift, by 64, because it's 16 times size of an int, which is 4. So it can do that automatically, and that simplifies things. But the more general case is that it's got to actually do an integer multiply, which can be an expensive operation, to compute the size, compute what, to do this product with C involved. And so that makes it more additional instructions, more cycles to do it. Okay? So any questions on that? Okay. So this, you can look at this at your leisure. Basically, this is just helps you with your understanding of how this all works. We've got this initialized array here. We've got different ways that we've referred to it. And then we have this funky expression that's really, bad code. But it does return 9. And the reason it returns 9 is highlighted here. That basically the thing in red gets you this digit. The thing in purple gets you this digit, and so forth. Okay? So you can look at that on your own and see, test your understanding of how these things play together. And again, it's a mess, right? C can be very much a challenge to understand how these things work. We want you to work on your understanding so you don't get tripped up. Okay, quiz time. Can you see it, or do I have to do something? Yeah, you have to tap that. All right, now it's closed. Okay, try now.
What is this one?
So let's do a little bit of arithmetic on these questions. All right, well, if some folks are finishing up. Let's see how people did. All right, so people did pretty well in the first one. Okay, I tried to trick you up a little bit by switching the roles of RDI and RSI in the examples we did. But basically, again, it's the long dictates why this should be an 8, and the you want the 8 to multiply by the index, not the base, and that's why it gets in that second position in the addressing mode. Okay, so here we have A, which is a array of 5 pointers to integers. So A is 5 pointers, each pointer is 8 bytes, and so it's 40 bytes. Okay, it's a little bit tricky. All right, this one people did pretty well on as well. Basically, because it's a long, it means we're jumping by 8 bytes at a time, and you want to compute, right? You want to be able to compute 1 times the size of each column in each row. So there's 6 columns, and each of them is 8 bytes. And then you want to go over 3 within that, and each of those are 8 bytes. Okay, so that's 72. Any questions on that? All right, good. So let's kill that. And go back to this. Okay, so let's talk about structures. So if you're familiar with C structures, this should make some sense here. So we have this structure, consists of these different things. The first thing is an array of 4 integers. So if we have a structure and it's initially addressed R, then we'll just look at the offsets from the beginning. So A gets laid out starting at 0, and it goes all the way to 16 because there's 4 of them, each of them are 4 bytes. Okay, so inside here, there'd be the 4 different integers. All right, I is laid out next, and it goes here, and then this pointer is laid out here, and we need 8 bytes for a pointer. Okay, and notice that they get laid out in memory according to the order in which you set them up here. Okay? Good. Now suppose you wanted to access somewhere within the structure. So let's suppose you wanted to access one of these array elements, like the indexed one. All right? Then, as shown, that gets computed as the start plus 4, since we're dealing with integers, times the index. Okay, so let's suppose you had some C code like this that was interested in looking at the, an indexed element off of the array, but then returning the address and not the element itself. So it's actually wants you to return this calculation. And so because you're trying to return the address, we're going to use this LEA and do the thing we've been doing before, right? 4, these get multiplied, added to that, and you get exactly this expression. Okay? All right, so this one's more interesting. So suppose we have this, a linked list of these structures, okay? And now what we're trying to do here is we have a routine that takes a the start of the linked list and wants to set each of the array elements to this val. Sorry, each to the val. So what's going to happen here is while this pointer that we're passing is not null, we want to set I to be whatever in here. So copy that, and then whatever items in here, between 0, 1, 2, and 3, we want to go reference that item in here and then set the val for just that particular item. And then we want to go to the next one. Okay, so depending what this I is, we will set a different element in that little array, and we'll proceed through the list until we hit the end of the list, in which case we'll get a null pointer and drop out of the loop. Okay, so R is going to be passed in RDI, and val is going to be passed in RSI, and the assembly code ends up looking like this. Okay, the first thing we're going to do is we're going to take 16 past R, right? And this is a move, so we're actually going to fetch what's there and put it in REX, okay? So R is here, 16 plus R is here, and so that has the effect of fetching this I and sticking it in this register. Now we're going to take the val, okay, which is in RSI, because it's only an int, we know it's only going to use up the first 4 bytes. We're going to use the shorter form of this expression where we use the long and we use the ESI, which is the lower half of RSI. Okay, so we're going to take that val and we're going to stick it where? We're going to stick it in this address here, which can be calculated as follows, right? So we have our I is here. We multiply that by 4, and we add it to R, which is still in RDI. Okay, so that's how we get the address. We store it into that address. Now we want to do this pointer chase. So we take the current R, and we the current pointer R, and we replace it with a pointer that's found 24 past R, which is basically this next pointer. So this has the impact of assigning R to be whatever the next was before. Then we have our test to see if that's a null pointer, and if it's not null, then we're going to loop again. Okay. All right. So that gives you a little bit of flavor of how these are going to look in your code if you write code like this, or you're asked to understand code like this. Any questions on this? Yes.
Isn't the length of I supposed to be 4 bytes? So like that was next to start it.
Excellent question. We're about to get to that. Good observation. So the question is, why did we set aside 8 bytes in this structure for something that we knew was only 4 bytes? Okay, eagle eye spotted that, and the answer is alignment. Okay, so we're going to spend the next few slides talking about alignment. So in aligned data, if you have a primitive data type that requires k bytes, then the address in which it sits in must be a multiple of k. So here's an example. So this is what it would look like if it was unaligned, if you just plopped them all down. Okay, that would be illegal assembly code, right? The proper assembly code looks like this. You have this character, that's fine. Now you look and you say, oh, I have this thing that's an array of integers. Well, I know I need 4 bytes for an integer. So back here, before I did the proper alignment, if I wanted to reference that integer, I had to reference this thing that was, p plus 1 to p plus 5. Okay, and that's more expensive to reference, turns out. So instead, you have this convention that it's got to be on a multiple of 4. So you start at p plus 1, you go to the next p plus the next one that's going to be multiple of 4. So here I forgot to mention that we're starting off, in this case, with p being a multiple of 8. Okay, so this will work out. So now this starts at 0, so this is 4, p plus 4, so that's a multiple of 4. So now I can lay out these two. And now I've got to come to this thing that's a double. So this double is 8 bytes, so I need to lay it out at some place as a multiple of 8 bytes. Well, this thing here isn't. This is p plus 12, right? And since p is a multiple of 8, p plus 12 is not. But p plus 16 is the first place that is a multiple of 8. And so again, I have this wasted space, and then I can lay out v. Okay? All right, so a little bit more on that. Okay, so this is talking a little bit about the motivation. The way the system, architecture is all about making the common case fast, right? And so the common case is that you don't have these weird structures and things are aligned. Like an array is a common case, right? You just, if it's going to be, an array of longs, it's going to be 8 bytes, 8 bytes, 8 bytes. As long as I start the allocation for this array in an 8-byte boundary, then everything's going to be aligned. And so when things are aligned, then I know I can just go and fetch it from memory. And I don't have to have in my architecture sort of the ability to fetch any consecutive 8 bytes starting anywhere, right? I can just say, okay, it's going to be this 8 bytes, this 8 bytes, this 8 bytes. And that's easier to implement, and that's the common case, so it can run fast. Okay? There's issues, for instance, that further issues about if you cross cache lines. So cache lines, we'll talk about caches later in this course. If you're not familiar with it, right? Typical machines have 64-byte cache lines. That's how things can move between memory and caches. And so again, if I don't do proper alignment and I happen to have something that's even though it's kind of small, actually crosses across two cache line boundaries, that's a mess. I've got to fetch 2 cache lines just to get the values I want. And that can cause all sorts of problems. And stepping up a granularity, the operating system deals with memory in 4 kilobyte pages, typically. And if you're not properly aligned, you might have some relatively small data item that spans 2 pages. And again, that's just a lot of inefficiency. If I'm going to have to fetch an entire page of something, and now instead of getting 1 page, I have to get 2 pages, even though I only wanted this little bit of data that happened to span 2 pages. So for all these reasons and others, aligned data is a good thing. The compilers know this, and so they automatically insert the gaps that we showed in the previous slide. Okay. So another way to think about the alignment requirements is shown in this slide. So if I have a character, fine, I can put it anywhere. If I have something that's 2 bytes long, like a short, then if I say it, the address must be a multiple of 2. That's equivalent to saying that the lowest bit of the address must be a 0. 4 bytes means the lowest 2 orders must be zeros, and 8 bytes, of course, means the lowest 3 orders of address are zeros. Okay, as long as that's true, then I know that address is aligned. Okay, any questions on that? All right. So let's revisit this example again. So given this, the compiler will lay this out such that each of the individual items get their proper alignment. Okay? But also, you need the overall structure to be placed in alignment boundaries. So the reason this ended up being multiple 8, I said this was placed in multiple 8, is because what happens is the compiler looks, and for each of these guys here, it says the largest alignment requirement, let's call that K, was multiple of 8. Okay, it happened to be this V. And so therefore, the initial address and the entire structure length must be multiples of 8. So the reason this has to be aligned to multiple of 8 is because K is 8 in this case. And this particular example would happen to end in a multiple of 8, but if it didn't, then the compiler pads it out to make sure it ends at a multiple of 8. So in other words, the next one wouldn't be able to start until the next multiple of 8. The next, whatever you're allocating. Whether it's an array of these things, and so it's just the next copy of the structure, or just whatever the next thing is. Okay? Questions on that? Yes?
So would that be true even if the last element were a char, just like to be safe, in case the next thing? So I guess
Yeah,
what I'm
yeah.
saying is the padding it to be a multiple of 8 doesn't have anything to do with the fact that the element itself was of size 8. It has to do with the fact that the next element could be size 8 potentially.
Well, so what we're doing is we're taking the max of all the alignment requirements, right? So it so happened here, the V was at the end. But if I'd reordered the structure so that maybe the V was in the middle, then, and these guys were at the end, it wouldn't matter. It would still have to be multiples of 8. Because it's based on the largest thing in there, not the last thing that showed up. Good. Other questions? Okay, so here's an example that the exact same structure but reordered, and so V came first. The integers need to be aligned at boundaries of 4. Turns out they're aligned at a boundary of 8, so we're good. Multiple of 8. So we didn't have any padding there. A character can go anywhere it wants, and so the only padding I needed in this case was to make sure that the thing ended at a multiple of 8, because again, 8 was the largest alignment requirement. Okay, so you can see that this was, went to P plus 24, and this went to P plus 24. So we're actually, in these two cases, it worked out. But you can imagine that you have, if you happen to lay things out in your structure in a poor way, you can actually create a lot more padding than otherwise. And so what the compiler will do, or so what you can do as a programmer is you can think about these and help the compiler by putting these in order that's conducive to less padding. Okay, or a really smart compiler might be able to figure that out as well. Okay. Yeah, this is just saying that if I have an array of these things, then again, by having them all be multiples of the right thing, then each of them will, right? I mean, so we said A0 has got to be a multiple of 8. And since this thing is a multiple of 8, then I know that the starting point here is a multiple of 8. And therefore, this thing, even though the layout is relative to one another, right? So the layout within this guy is just relative to itself. It all flows together nicely because of the fact that this ended at the right multiple. And so then this one knows it starts at the right place and so forth. Okay, so you pad out arrays to make sure this happens according to the rules, and then it all works out nicely. Okay. Good. And similarly, based on the padding, will affect the addresses you see. Okay, so you may see unexpected addressing because if you don't account for the kind of padding that's going on in your structures. Okay, so that's something to watch out for in your code. All right, you can see that in this example. I won't go through it. Oh, the only thing that's interesting about this example that I haven't covered yet is that this thing here, it shows as 8 plus 8 as the offset for the thing you're interested in. And we're used to seeing just like A, but you can also do expressions such as this, and the linker will resolve all these addresses. So before the code actually gets executed, this will be replaced by just a single number, right? A single address. Okay. So it's kind of what we've seen before. We've had the shorthand that we just put an A here, and we know that wherever A gets loaded in memory, that's the address that will be put there by the time the code executes. This is just showing that you can do a little bit of arithmetic on the way as well. And so you might see that in your assembly code. By the time it gets to the machine code with the bytes and such, and gets all linked, then that'll be going. All right, so here's what I was touching on earlier. You can save space. A good rule of thumb for saving space is it always works if you put the largest data types first. Okay, so in this case, since int's the largest one, you put the largest one first. It leads to no worse padding. Right? You can, if you're so inclined, you can try to prove that for yourself formally, but it works. Okay. So this is the kind of question that we'd love to throw on the midterm, and potentially on the final, right? So we'll give you one of these structures, and we'll say lay it out in memory. Okay. And so you come and you say, oh, I've got this car, so I'm going to put it here. And then I've got this long, and what do I know about longs? Right? They got to be multiples of 8. So that means I've got to go, it says 1, 2, 3, 4, 5, 6, 7. Did I get enough of them? And then I can start B, right? 2, 3, 4, yeah. So that's a multiple 8. So longs take up all 8. And this is just, think of this memory as just wrapping around. It just wouldn't fit on a page if we ran it off this way. So now I've got a float. So it needs to be a multiple of 4. Well, I've got that, right? It's a multiple 8, so I've got a multiple of 4. Now I've got a car. All right, what are the alignment requirements on car? Can go anywhere, right? So this is D. Got 3 of these. Now I've got a pointer to an int. So what multiple do I need to align that on? 8. All right, so I need to do it here. That's the next multiple 8, so that's padding. Then I have a short, so that's just going to take up 2. Oh, sorry, no, it's a pointer to a short. So how much is that going to take up?
8.
8. All right, now do I need to add any padding at the end? So a common mistake is to forget about padding at the end. Do I need to add any padding at the end of this? No, because this is, I mean, the multiple 8 boundaries are here and here, right? So we're good. And the largest thing was multiple of 8. Okay? All right, so that's just what we went through. All right. Then the question will say, okay, now let's be smart about it. Let's rearrange the elements to do better. Okay? And so here you figure out, okay, what's something that's, there's more than one answer to this, of course. But let's take the first thing that's requires an 8-byte thing, and that'd be B. So I put that first. 1, 2, 3, 4, 5, 7, 8. Right? And now let's find another thing that's long. How about these pointers? All right, I put the pointers next. And then the other pointer. All right, so now I'm done with that. Then what's next? I guess maybe the float. It's the next largest. Okay, and now I've got these cars. Okay, A, D, D, D. All right, and do I need to add any padding? No, so you can see it compared to this, it's a lot better, right? So you're ready to make any mistakes. There we go, good. Okay, any questions on that? Yes?
So when we actually declare we actually declare star of E, then when will that be? Like will it be after F or
Will it be,
like will it be after F? Will we declare like the values from
if you, so well this is just a type def, but somewhere in your program you have, foo, you have type foo, and let's call it, my foo, right? And so, and then maybe right after that in the program, maybe you say I have an int, and it's, x, right? So it will lay out foo, and then it will lay out x right after that. Good. All right. Real quickly, we've got a few slides on floating point we need to finish. So floating point, SSE is the type that's supported on the Shark machines. The more recent Intel machines have something called AVX. The main difference is that the Sharp machines, the SSE instructions, have 16 byte registers, whereas the AVX has double that. They have 32 byte registers. And there's a nice figure in the book of that. So there's separate registers. Thus far in this course, we've only been talking about integer registers. The floating point registers are all have names XMM0, XMM1, and so forth. There's 16 of them all in all. Now, an interesting thing about them is that they're 16 bytes long, but the program is allowed to, and instructions will look at them, and it's allowed to think of them as a bunch of smaller registers. So, for instance, I can take a single 16-byte register. This is one register. Let's say this was XMM0. Okay? I can think of that as storing 16 different single-byte integers. So if I have a bunch of small numbers, 3, 4, 1, 2, and so forth. Okay? And I can operate, there are instructions that operate independently on each of these. Or I can think of that as 8 16-bit integers, so a couple of shorts, right? Or 4 32-bit integers, right? So I could have my normal int in each of these places, right? And it's just a way of introducing sort of SIMD-style parallelism, right? I can now do a single operation on 4 ints at a time, 4 32 bits at a time, or a single operation on 16 single-byte integers at a time. Similarly, you can do the same thing for floats. You can have 4 single precision floats or 2 double precision floats. If you don't want to use the parallelism, you can also just do, based on the instruction, they will just use the first 4 or 8 bytes in the register and ignore the rest. Okay? So it's a little bit, takes some getting used to, but it's nice if you ever have a lot of SIMD parallelism you want to take advantage of. And that's done through these operations. You can do an operation that just combines 2 registers, like this operation here, takes the quantity in this register here and adds the quantity of this register and stores it in here. Okay, that's kind of more what we're used to. But if you have this P here, then it says, oh, I'm going to take 4 of these guys and do that same operation in parallel. Okay, and similarly for double precision, there's a version that just does the low order parts, and there's a version that does both of them at once. Okay. If you have function calls, remember we've been talking about the integer arguments, and the first 6 are passed in registers. Here, the arguments are also passed in registers, but they're passed in the XMM variants of these registers. And instead of returning an RAX, the return result is in, if you're returning a float, is in the 0th XMM register. And all registers are called LUR saved, right? If you want the value when you come back, you better scroll away somewhere. Okay, good. And memory referencing is very similar, but it has special opcodes that deal with the floating point versions. But conceptually, it's actually pretty much the same, right? You do a move, you give it an address, and you move it into another floating point register. And then there's the ones that sort of do conversions, like if you go from a floating point register to an integer register, and so forth, and there's different opcodes for that. But it all works out. It's all sort of the same notion. You've just got to get used to seeing 2 different things. One is the use of floating point registers instead of the integer registers. And the other is that these SIMD instructions, so you can do a bunch of things in parallel at once. Okay. So I don't think in this course you're going to use these in any of your assignments. But maybe you can find a way in one of the later labs to speed up code using these. Could be interesting. Okay. Tons of different instructions. Again, we're not highlighting that much in this course, including comparison instructions, constant values, and so forth. Okay, so that's today's class. We talked about arrays, structures, and floating point.